Welcome to Oceans Part 2. We left off taking a look at the nature of seawater, so I've put all of that back up on the screen for you. Um, Talking to you specifically about the fact that the seawater is typically between 35, is about 35% on average by mass is the concentration of salt in seawater. So here are minerals in the seawater. If we have, mostly it is chlorine, which means that mostly you've got sodium would be part of that as well, sodium and chlorine. So here's the orange is sodium here, and this blue is chlorine, and that's because most of the salt, which salt is really just an ionic compound with a metal and a nonmetal. But the biggest ionic compound that's in the ocean would be sodium chloride. That's the most salt. But then there are other salts as well. You could have magnesium chlorides, calcium chlorides, magnesium. I already said sulfur. You've got some sulfur in seawater. So this is what we find in seawater. Okay, but the bulk of the salts that you find in ocean water is, of course, sodium chloride. Seawater moves. So it's in order for a complete mixing of all of the Earth's oceans, it'll take about 2,000 years. Um, but the movement is constantly taking place. We have waves, multiple types of waves, and then we also have currents that are caused by multiple things as well. Remember, we've talked about waves, surface waves, which are caused by wind, but then you can also have waves underneath the surface, which could be caused by any number of things. Underwater disturbances and whatnot like that, displacements of water creates a wave underwater. Then we could also have currents. Currents could also be caused by wind if they're surface currents. But then you could have currents underneath the water, rivers essentially running through the under the water that are caused by changes in density due to temperature, salinity, and that sort of thing. There are massive currents moving, general currents that move on a regular basis as a result of changing salinity. If water it decreases its temperature or increases its salinity, it becomes more dense. And as it condenses, it moves, and as it heats up again, it rises and it evaporates and becomes more saline, and it drops again. And so you end up with these big movements that are essentially like convection currents moving in the water on a regular basis. But again, you could have currents by wind or currents that are caused by either convection or changes in salinity. So waves, you could have, just if you remember in our previous lectures about waves, we have wave height, wave length, and wave period. So depending on the type of wave that you have, the wave height is of course the amplitude, the distance from the center. Wave length is the distance from crest to crest or trough to trough. And then the wave period is how long does it take for a whole wave to get past, which means that the frequency would mean how many crests are passing in 1 second. So if you've got a really windy area, you might get a whole bunch of successive waves, or they might add up, and then you end up with multiple large waves. So if the wind can blow across a large area of water, you could end up with very large waves. Or if you have if you have wind only blowing over part of the surface, then you're going to get smaller waves. And so we've talked about all in previous lectures. We've talked in several previous lectures. In fact, we've talked about wave length, wave height, and the vocabulary dealing with waves. So ocean waves from wind. So wind moving across the surface of the ocean is definitely going to cause waves. They carry the energy but don't transport the water. And we've talked about that. And the individual particles are moving in a circular motion. The wind speed, the length of time that the wind blows, and the open surface that it has to work on will be the factors that determine how large these waves are. Typically, from wind, you're going to get a very complicated mixture of wavelengths and heights. Small waves dissipate from friction in the water. Larger waves may last longer, travel faster, and eventually coalesce into a large swell. How does this affect the shore? Okay, waves coming into the shore at an angle. If waves hit things like landforms, sandbars, that sort of thing, then they will diffract across as they move in. Okay, so as they come into shore, they may refract they may refract as a result of changes in temperature and that sort of thing. But if it's moving around things that are solid, then that's more like a diffraction. And so you could end up with waves moving apart and then coalescing, coming back together. So you get wave fronts that bend towards the shore as they go around something. When the wave comes into shore, once it reaches a point where you end up with more wave out of the water than in the water as it's going through, then the wave will start to crash, and that's where you get these breakers. Undertow is when the water returns back out after it crashes on the land and comes back in. And then you could also have something called a longshore current, which is a motion parallel to the shore. So as the longshore current moves along the shore, it could produce some riptides whenever there's a channel. So if it as it's moving along the shore, you could end up with places that literally it's resulting from a change in pressure, water pressure, as the water is moving very quickly, and it could end up pulling water back out. And when it pulls water back out, that is called a rip tide. Here you can see some rip tides in the water itself. So a rip current is a strong stream of water pushing out against the waves. Usually this extends beyond the surf zone and then diminishes. You can always tell, and you can see if you've got a longshore current, you could end up easily with a rip current. So that if you end up with darker water or a deeper channel moving away from the beach, then this is a rip current. A lot of people drown in rip currents every year. The best thing to happen if you get caught in a rip current pulling you out is to swim parallel to the beach, and then you will swim out of the rip current, and then you're able to then swim back to the beach. Ocean currents themselves, there are some massive ocean currents that move lots of ocean water up and down the coastlines. The Gulf Stream, for instance, is one. The Gulf Stream is responsible for taking a great deal of energy up the eastern coast of the United States and across over to Europe. If it were not for the Gulf Stream carrying a great deal of energy into Europe, then the UK would be a whole lot colder than it currently is. Ocean currents typically are caused by density differences in seawater, either as a result of salinity or temperature, and winds blowing persistently in the same direction. The Earth's winds are constantly blowing in a particular, the overall wind patterns blow in a particular way, and we'll see that when we start talking about the weather. Density currents occur when you have changes in salinity or changes in temperature. So changes in temperature result in convection currents, and so when you have water that's extremely cold, it becomes more dense and drops. When water is heated up closer to the equator, it becomes less dense and it rises, and so you have this constant convection of water rising at the equator and dropping at the poles. Well, add that in with the fact that the Earth is constantly spinning, and so we end up with moving Earth currents. And so the currents are actually because of what's called the Coriolis effect, and mostly we talk about that with winds, but it also affects the ocean. It also affects the currents in the ocean. So you're going to end up with currents moving either towards the east or towards the west as a result of this major convection that's happening. Salinity also occurs and changes in salinity due to evaporation, causing water to become more saline, and then rainfall, which causes it to be less saline. The more salt content, the higher the salt concentration, the more dense the water, and that will sink. More rain means you have more fresh water and you have a diluted solution, and so that becomes less dense and it rises. So just like with the temperature, you end up with essentially a convection, only it's changes in density due to salinity. And these are causing major ocean currents. These things will, along with suspended sediments, which has the same effect as the salinity. When you have more sediments in the water, it's going to become more dense and it's going to sink. So in each one of these cases, changes in density are creating this current. Something is more dense, it falls; less dense, it rises, and so you end up with water moving essentially in a chain. And then as the Earth is actually rotating, you end up with currents in the ocean. And here we see that sort of thing. As water is cold dense water drops. Cold dense water drops, and as this goes south towards the equator, it rises because it gets hotter. Surface currents are broad and deep running ocean currents that slowly move tremendous volumes of water near the surface. Typically they are caused by the wind. Typically they are caused by the global wind patterns. As the wind runs across the surface, the friction is going to drive these currents. You could actually have something called a gyre, which is a system where the water runs in a circulation. And this is usually centered around the middle latitudes, and so you could end up with a large rotation of the water as a result of the surface winds, which are doing the same kind of a thing. And so you could end up with water that's moving essentially like a big whirlpool, although it's not really moving like a whirlpool. So here we have a diagram with the Earth's major currents, and you can see how they are going to curve. So here's the Gulf Stream moving up this way. And you can see on the other side, it's a current that's moving in exactly the opposite direction. And notice the Gulf Stream is bringing warm water up from the equator. The current on the other side is moving south, so that's bringing cold water down. This is why water on the west coast of the United States is always cold, whereas water on the east coast tends to warm up. If we think about the ocean floor, we already know that the ocean floor is made up of oceanic crust. The oceanic crust comes into contact with continental crust, and we call this the continental shelf. So coming out from the east coast of the United States, the continental shelf runs a long way out because the North American plate goes a long way out, as a matter of fact, all the way to the middle of the Atlantic Ocean. So you've got a very gentle slope going out towards the end of the crust, the continental crust, on the Atlantic side. The Pacific side, however, you don't. On the Pacific side, the North American plate butts right up against the Pacific plate, so you don't have a great deal of continental crust moving away from the continent. So as a result, the slope on the west coast is far steeper than the slope on the east coast. This is also why you end up with much larger waves on the Pacific coast, because they have a wave has to come way further inland before it crashes, before you get breakers. Whereas on the east coast of the United States, it gets much shallower much quicker. The ocean basin, this would be primarily where you're going to have nothing but oceanic crust, and this would be the deepest parts of the ocean. This is characterized by what's called a level abyssal plain. Trenches can also occur along these edges. This is subduction zones. Remember when we talked about in a previous lecture, we talked about where oceanic crust and oceanic crust come together, and one will be subducted under the other, and we could have trenches. These are like the Marianas Trench in the Pacific Ocean. This is where two bits of crust come together and one is subducted under the other, and you could end up with some of the deepest points in the ocean. You could have volcanic peaks scattered throughout and seamounts up underneath the ocean throughout, depending on where there was volcanism. The Hawaiian Islands are a product of volcanism, and those were seamounts at one time before they stuck up over the water, and now we have them as islands, and those were created by hot spots in the Pacific, in the middle of the Pacific Plate. And here you can kind of see that. So if we were on the east coast, this continental shelf would extend out way further. The continental slope would be much more shallow and whatnot, but here, if this was the Pacific side, you can see kind of what's going on. So we have land, we have continental shelf, and it doesn't take very long on that continental shelf before we have a very steep continental slope. We have the abyssal plain, and we could have some seamounts and ridges, and then the volcanic islands, and so here we have a volcanic island right here. So let's go back over to the Atlantic coast, the Atlantic Ocean, the Mid-Atlantic Ridge. The Mid-Atlantic Ridge is a spot where we have oceanic crust that is moving apart. Okay, the oceanic crust is moving apart because of the fact that you have, as the ocean is pushing up, or the oceanic crust is moving apart, and then you have magma coming in the middle and pushing it apart, and so it's this rift is constantly getting new rock, and so the area here in the middle is much younger rock, 0 to 5 million years, much younger rock, and the closer we get towards the continents, the rock is much more older. And so when we drill in these areas, we do get evidence of the fact that the rock is getting older as we get towards the continent, and much younger in the middle here as it's, as the rift fills up and moves outward, and so on and so forth. So what that means is that North and South America are constantly moving away from Africa, which means that on the Pacific side, we're constantly pushing both sides of the Pacific crust together. So we have oceanic ridges that coincide with submarine earthquakes. We do have rifts along this crest. Large amount of heat escapes from this crest. And when we take a look at the age of the rock along the Mid-Atlantic Ridge, we find that directly along the ridge we have rock that's far younger than the rock that's closer towards the continents. And here is our Mid-Atlantic Ridge. So on the Atlantic side, most of our volcanism takes place down this ridge line right here, which this is what marks the difference between the North American plate and the Eurasian plate and the African plate. Whereas over on the West Coast, the continental plate line is directly next to the coast itself and covers the entire Pacific Ocean. And that's why we get our volcanism closer to land over on the Pacific side and all the way around what's referred to as the Ring of Fire. We can also take a look at the pattern of metals, magnetic rock, in each one of those stripes that we see moving along the edge of the rift, the Mid-Atlantic Ridge. because you can see magnetic reversal patterns in those rocks. Remember, let's think back to what causes magnetism when everything lines up. Well, when we see those patterns of lined up metal particles, we can actually see where that they were together at one point in time and now they're farther apart, and this is happening because of the seafloor spreading in the middle of the Mid-Atlantic Ridge. So when those patterns match, getting closer, and those patterns match moving further and further out, we can tell when they were together, and that's kind of a cool thing. So that's just plenty of evidence that we know that the seafloor is actually spreading. So the oceanic crust is kind of like a big conveyor belt that's moving North and South America away from Africa, about the same rate as your fingernails grow. And so here you can see a diagram that's showing that. So as the plates move apart, and so here this layer moves apart and new layer forms between it. That layer moves apart and new layer forms between it. That layer moves apart and a new layer forms between it. So you can see the tan, this tan would match this tan. This brown would match this brown when we look at not only the magnetic patterns and whatnot, and then the blue matches the blue, and so we can see what's going on there. So here are some study websites with ocean floor spreading. Again, your information for the middle grades gaze, and with that we will bring oceans to a close.